Freezing point, depression, boiling point, elevation. These are colligative properties. Colligative properties is a collection of properties that depend on the number of dissolved particles. It doesn't matter what the particles are, it's just how many dissolved particles are there in a given volume. So if you add a non-volatile solute like sodium chloride to a liquid, it will extend the temperature range over which that liquid remains a liquid. So you add ethylene glycol, which is a non-volatile liquid, to the water in your radiator. It expands the temperature range over which the water remains a liquid. It lowers the freezing point and it raises the boiling point. So these effects are called freezing point depression, because that goes down, boiling point elevation, because that goes up. In the Midwest, where I grew up, they get a lot of ice on the roads in the winter, and so they put salt on the roads. That lowers the melting point of the ice and causes it to melt sooner when it's cold outside. You put ethylene glycol in your radiator to raise the boiling point of the water so that your engine doesn't cause the water in the radiator to boil and your radiator to spew steam on the side of the road. So these effects, these colligative properties, because they depend on, start that over again. We don't use molarity when we calculate freezing point depression or boiling point elevation. We use another unit that I consider to be just crazy, but it's there and we have to deal with it. It's molality. So molality, molarity, one letter different. I'm sorry, I would have named it something else, but there it is. And the abbreviation, lowercase m. Really, we already used that for moles. I mean meters. Now I'm mixed up too. So there's way too many m's in chemistry. But anyway, this is what it is. We have to deal with it. Molality, lowercase m. It's an italicized m. Yeah, good luck with that with handwriting. Anyway, molality is moles of solute, but instead of liters of solution, it's kilograms of solvent. So that's an important distinction. Kilograms of solvent, not kilograms of solution. The other things we've talked about, percent by mass and molarity, all had to do with a quantity of solution. This one's different. There is a reason for that, and the reason is that molality does not change at all with temperature, whereas molarity can change with temperature. So let's calculate the molality of a sucrose solution containing 50.4 grams of sucrose in 0.332 kilograms of water. So molality is moles of solute per kilogram solvent. So we need moles of sucrose. Well, they gave us mass. 50.4 grams of sucrose. Let's see if this number is still in my calculator. I think it was 342. So many calculations today. There it is, 342.3. So we need moles of sucrose from grams. 1 mole, 342.3 grams. I got this number from a previous calculation. You just take the formula and calculate the molar mass. So 50.4 divided by 342.3 to get the moles, 0.14723 moles of sucrose. So that's what I need in the numerator, 0.14723 moles. And 0.332 kilograms of water. Water's the solvent, so we don't have to do anything to that. 0.332 kilograms of the water. And so we come up with 0.443 script M, molality. Any questions? Molality calculations are not a huge deal in Chem 3A. The only reason we talk about them at all is so we can calculate freezing point depression and boiling point elevation. So the freezing point depression, the amount of change in the freezing point is equal to the molality of the solution times a constant. That constant is going to be different for each solvent. So you would just look up KF in a table. I don't know anybody who has those memorized. And you find the molality of the solution. It may be given to you. You may have to calculate it. And then you can calculate the change in the freezing point. So calculate the freezing point of an aqueous 2.6 molal sucrose solution. And here we're given the freezing point depression constant. So the change in the freezing point, delta TF, equals the molality times the freezing point depression constant. So the molality was 2.6. Molal means moles per kilogram, times this constant, 1.86 degrees Celsius times kilograms divided by moles. Now there's a typo. See the mistake in the question here? It isn't moles of solvent. It's moles of solute. So 2.6 times 1.86. So this equals 4.836. Look what happens with the units. The moles cancel, the kilograms cancel. I'm left with degrees Celsius. If I consider significant figures, I should have 2. I have 4.8 degrees Celsius. Is that the freezing point? That's the change in the freezing point. Okay, we calculated delta TF. This is an aqueous solution. What temperature does water freeze at? 0 degrees Celsius. The freezing point change, the freezing point depression, is 4.8. So that means the actual freezing point is negative 4.8. So this is the freezing point depression. So that the freezing temperature goes down. So the freezing point is what it started out as, 0 degrees Celsius for the pure solvent, minus the change in the freezing point, 4.8. And so the actual freezing point is negative 4.8 degrees Celsius. Any questions? If we add a solute to a solution, we can raise the boiling point. So the freezing point goes down, boiling point goes up. It's important that it's a non-volatile solute. So antifreeze in your radiator prevents the water in your radiator from freezing in a cold climate and from boiling over in hot climates. Here we don't care so much about things freezing because it never really gets cold enough to freeze the water in your radiator. But in Minnesota, it does. Water expands when it freezes, and if you just have water in your radiator, it's going to freeze solid and blow out your radiator. The calculations for boiling point elevation is essentially the same, just change the subscripts. The change in boiling point temperature is the molality times a constant. Again, the constant depends on the solvent. You look it up or you're given it. And I made the same mistake on this slide, probably because I copied and pasted. It's not moles of solvent. It's moles of solute. So we're asked to find the boiling point. Well, first calculate the boiling point elevation, the change in the boiling point. The change in the boiling point equals the molality times the boiling point elevation constant. So we're given the molality 3.5 moles per kilogram multiplied by this constant 0.512 degrees Celsius times kilograms divided by moles. The kilograms cancel, the moles cancel. 3.5 times 0.512. So the change in the boiling point is 1.792 degrees Celsius. Does that mean the boiling point is 1.792? No. Water doesn't boil at 1.792 degrees Celsius, even if you put some sugar in it. That's the change. The boiling point goes up. So the new boiling point is the original boiling point, which is what? 100 degrees Celsius, plus the change. So 101.792 or 101.8 degrees Celsius is the temperature at which the water will boil. Any questions? Yes?
So to calculate the temperature or the boiling point, there's no like initial or final calculation?
Yeah, so that is confusing because I've tried to drill into your heads that delta means final minus initial. For these calculations, the change in the boiling point, the change in the freezing point is always going to end up being a positive number. And so you have to use common sense and add to the boiling point or subtract from the freezing point.
So you add from 100 for boiling or subtract from 0?
Right. So, I used to have a hard time remembering. I knew one went up and one went down, but which is which? So many things in chemistry. You've got these two pairs, but how do they go together, right? You can get them backwards. So it extends the range over which it remains a liquid. So you think about your radiator, you've got water in there. You want it to be a liquid. You don't want it to boil too low or freeze too high. This makes that range over which it's a liquid larger. So boiling point goes up, freezing point goes down. They move away from each other, if that helps.